Hello, guys. Good morning. Good morning to all of you. Welcome to another session. Today we'll be discussing the remaining topic of LSDG coupling and term symbol we have already covered. Just a moment. Is the audio and everything all right? Audio is the most important thing. Is the audio and everything all right? It is fine from my side. Let me know if it is also fine from your side. Okay. So let us start with this homework problem I gave you on the last day. How much does the total angular quantum number J change in the transition of CR3d6 as it ionizes to CR2 plus? Okay, so we have been given this chromium atom and the outermost cell electron configuration 3d6, and it has been ionized. Ionization, it has undergone ionization, and it is converted to CR2 plus, becomes 3d4. In this process, how much this J value changes, that you have to decide. So if we can evaluate the J values individually for 3d6 and 3d4, then it is our job is done. So have you tried this problem, guys? What answer did you get? A, B, C, D? Which one you get? Or you haven't even tried this? Have you tried? One, two, three, 5. D, we can write the ml values. -2, -1, 0, +1, +2. Right? 3d6. 1, 2, 3, 4, 5, and 6. So what will be ms, you know? What will be your s value? Sum over ms. So this is pairing, and this half integral, this half values, 4 half, that is 2. And what about L? Sum over ml, and as you can see, how much it is? 2. Okay. And this is what kind of cell it is? It is more than half filled. Highest J value, you need to calculate the highest J value, right, to get the ground state. What is the highest J value? L plus S, you know it. Modulus of L minus S to L plus S, so highest J value is L plus S, 2 plus 2, 4. So the ground state spectroscopic term, ground state spectral term, What is that? 2s plus 1, 5. L equals to 2spd, 4. So here j value is 4. Okay, this one you need to know. Now let us talk about 3d4. So what changes you can expect for 3d4, 3d4? So almost things will remain same. Few things will be changed. (3d4) means this will be filled up, this will not be there. Okay, what will be your ml ms values? We need to calculate the j values. Okay, so first of all, L sum over ml, and as you can see, what is the value? Again it is 2. We should have taken, look, it will be better if you take a negative value, we can take to be positive. Okay, no issue. Then we have S sum over ms, 4 half 2. Now this is the case of less than half field. For less than half field, we know inverted order will appear. So we need lowest j. Okay, we need lowest j because this is less than half field. So we have to consider the inverted order as far as Hund's rule is concerned. So lowest j value will be here L minus S. So this will be 0. So here what will be the ground state term? 2s plus 1, 5. So 5 d 0. Therefore j value was 4 and it has decreased to j equals to 0. Okay, so decreases by 4. Option C. J value decreases by 4 unit. How you get ml values? Ml values, for a particular L value, ml values are given in this way. For an example, if you consider p orbital, it may be p3, p2, p1, whatever it is. How many subcells are there? 3 subcells. 1, 2, 3. So p is designated by L is equals to 1, right? So the values will be ml values, minus L less equals to ml less equals to plus L. This one right? So that is why minus 1, 0, plus 1. Now when you consider d orbital, 1, 2, 3, 5. For dspd j1, 2. So it will be ml value will be from minus 2 to plus 2. So minus 2, minus 1, 0, plus 1, plus 2. If you consider F, there are 7. 1, 2, 3, 4, 5, SPDF L equals to 3 minus 3 to plus 3. Yeah, you can also write that in that way also. If we do minus and instead of minus, if we do plus, that will not change anything. Okay. See, is it changing anything? Okay, it will be better if you write plus. So you stick to 1, whatever you have done, stick to that. Okay. So if you have written plus first, you can write that. In some books, they write plus first, then minus. And in some book, they just do the reverse one. So you don't get confused, just do it. Okay, plus 1 first, then the negative 1. And that will help us in calculation also. Okay, this one is good. Should we get add only unpaired cell to no. You see how ML is coming. If I talk about here, plus 2, plus 1, plus 0, minus 1, minus 2. Okay. So this, then the pairing for pairing also it is plus 2. That is why we ultimately get 2. Okay. Here, how to get it? So whatever you know, this is there is a rule. The electrons will fill first singly. Okay. Then they will make pair. So you will consider it in this way. Although we are seeing a pair, but you will consider it this one first, plus 2, this one plus 1, this one 0, this one minus 1, this one minus 2. Then we will come back here. For the down one, the ML value is plus 2. Okay, so that is why we have written this plus 2 here, and this plus 2 is for this. Okay, for this one plus 2 plus 1 plus 0 minus 1 minus 2, and that gives you 2. Okay. For MS value, you know, the values are plus minus half. Okay, so for this value is half, this value is plus half, this value is plus half, this value is plus half, and for them, look, they say this value is plus half, 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 and this one it is minus half. Okay, so 1 plus half is cancelled, and remaining 4 plus half is added. I think everything is all clear now to everyone. Vantage, Murli, Harry, Ajay, everything is all right? All clear? Yeah, sound went by. Now, is everything all clear? This doubts, sound and everything? चलिए आगे बढ़ते हैं. The ground state electronic configuration of the rare earth ion Nd3 plus is this. Assuming LS coupling, the Lagrange factor is 8 by 11. The effective magnetic moment in units of Bohr magnetron is. What you have to find out? Magnetic dipole moment, mu j, you have to find out. You already know the formula of mu j. You know it now? Gj mu b j by h cut, right? Now j value we already know quantum mechanically. J into j plus 1 square root h cut, right? So do this one. Now which one you need to consider, F3, S2 or P6 to evaluate the ground state? F3, S2 or P6? F3, good, do. So calculate the J value corresponding to the ground state and just use the formula, you will get the magnetic moment. So here we have to deal with 4F3. F, how many subcell it has? 7, right? Plus 3 plus 2 plus 1 0 minus 1 minus 2 minus 3. F3, 1 electron, 2 electron, 3 electron. Okay, so you got the value of S. Let's calculate the value of L. L is sum over ml, 3 plus 2 plus 1, 6. S sum over ms, so 3 halves, 3 by 2. So this is less than half filled. For less than half filled, you know, inverted order. Inverted order means highest J will lie lowest. Okay. So what is the value of L plus S? Look, the values of J will go from L minus S to L plus S. Okay, less than half filled normal order, sorry, not inverter. Inverter order for more than half filled. L minus S So 9 by 2 plus 1, 11 by 2 plus 1, 13 by 2 plus 1, 15 by 2. So we need to find less than half fill in normal order, lowest j will lie lowest. So lowest j 9 by 2. This will be the ground state j value. The j value corresponding to the ground state. The effective magnetic moment in units of Bohr magneton. So therefore the magnetic moment, therefore the effective magnetic moment, we have to find it in units of Bohr magneton. So we are using this formula of mu j. We are not writing the vector sign. Mu j is equals to gj mu b times j by h cut is root over j into j plus 1. H cut is getting cancelled. So gj is given to in the question 8 by 11, and mu we have to find out in terms of mu b. So j into j plus 1, so root over 9 by 2 into 9 by 2 plus 1 times this mu b. Inverted case for more than half field. Yes. Here normal ordering, less than half field. This is a normal case. Lowest j will lie lowest. And if you calculate, how much value will you get? 3.618 times mu b, approximately 3.62 mu b. Yeah, matching with option 1. Clear? Okay, so from the previous lessons also, let me give you a brief summary. How 8 by 11 comes? It is given in the question. A land degree factor for this one is 8 by 11. So we have evaluated the terms for various orbitals, okay, various electron configuration. So let me just give you a brief summary. So you can make a table like this. Here in one side we can write the corresponding electron configuration, and here we will be writing the terms, electron configuration, and here we will be writing terms. Total 7 rows we require. This is 7 rows. So firstly, if you consider S1, we got the terms 2s half. So this is a brief summary. If you do not need to write, you may not write. Okay, this is just for whether you call S2 P6 D10. So these are closed cell, right? For closed cell, what is the term you get? 1s0 every time. Term for P1 and term for P5 will be same. You will get 2p half and 3 by 2, 2p 3 by 2. Term for P2 and P4 will be same. You will get 1s0 term, 1 D2 term, 3 P 0 1 2. These are all equivalent electrons, okay? There is a slight difference between J and G. Here this capital L, S, J, these are quantum number, right? And this J is the angular momentum, and this small j and this capital J are same. They are quantum numbers. Murli, when we are writing capital J, we can write it in this way: root over j into j plus 1 h cut. So this j is the angular momentum. Angular momentum, and then this j will behave like a angular momentum quantum number. Now if I write both plus j, it looks odd. So that is why sometimes we write a small j. Okay, no issue. It's up to you how you treat. P3. For P3, we have got terms like 2p half 3 by 2, 2d 3 by 2, 5 by 2, 4s 3 by 2. Now the term for d1 and d9 will be same: 2d 3 by 2, 5 by 2. Term for d2 and d8 will be same. The terms are 1 is 0. You don't need to remember, okay? I'm just giving you, just for the sake of completeness, I'm providing you the list. Otherwise this list is not necessary. If you want, you can ignore this list. Now, okay, these things, these terms we get when there is no external electric field or magnetic field. Now let's say you have got these terms, and on the previous day we have told you how this unperturbed level, let's say for 3p3d, unperturbed level is split into different parts, okay, and you got these terms. Now these are the situation when there is no external field present. Now if if external field is present, what happens? Each j value, each level which is designated by j value is splitted into 2j plus 1 number of levels. Okay, so that is what we are going to do. That is called degeneracy. The degeneracy is lifted. Degeneracy was there, but the degeneracy is lifted means it is splitted into various levels by the application of the external field. It may be magnetic field, it may be electric field. When you talk about magnetic field, we get G-man effect and all. When it is electric field, we get a Stark effect, you know. So let's take an example of two non-equivalent electrons, 3p, 3d. So this represents non-equivalent electrons, right? So for the first electron, if I talk about the value of L1, L1 is 1, L2 2. Similarly, S1 is half, S2 is half. Both are electrons, so S values will be same. And from this we get the value of L, which is between L1 minus L2 to L1 plus L2. So the values will be, you see, 2 minus 1, 1, 2, 3. And the values of S will be similarly S1 minus S2 to S1 plus S2. So this is 0 and 1. Now these are non-equivalent electrons, so there is no restriction that even will combine with even, odd will combine with odd. There is no restriction, even can combine with odd also. So if you consider S is equals to 0, it can combine with L is equals to 1, L is equals to 2, L is equals to 3, and this can give you J is equals to 1, J is equals to 2, J is equals to 3, and you get the terms. You get the terms here, 1 P1, 1 D2, 1 F3. Okay, then we take X equals to 1, L is equals to 1. We get the value of J to be 0, 1, 2. Okay, we get the term 2s plus 1 is 3, L is P, L equals to 1 P, 0, 3P 0, 3P1, and 3P2. Then we take L is equals to 2. We get the value of J to be 1, 2, 3, and we get the value 3 D 1, 2, 3. Okay, then we take L is equals to 3, J is equals to 2, 3, 4, and we get the terms 3 F 2, 3, 4. Okay, now if I apply the magnetic field, if you apply magnetic field, then what will be the degeneracy? If I talk about the degeneracy is 2J plus 1. So for this, the degeneracy D will be 2 into 1 plus 1 is 3. For this one, what is the degeneracy? 5. For this one, what is the degeneracy? 7. 3P012 and so on. So what will be the degeneracy values here? 1, 3, 5, 3, 5, 7, 5, 7, 9. So if you consider the total degeneracy, what will be the total degeneracy? Just add all the numbers. 8, 15, 16, 19, 24, 27, 28, 36, 41, 40. You will get around 60. Look, the main thing is each level is designated by different values of J. And in presence of magnetic field, they will split into 2J plus 1 sublevels. Each level, each sublevel will be designated by Mj, and Mj will run from minus J to plus J. So total 2J plus 1 values. The total number of degeneracy, the total number of degeneracy of 3p 3D is 60. I'll share with you a short trick to find out this total number of degeneracy in a short way. You add all this number, you will get 60. Okay. Now I don't have space. I am giving you the short trick here. Here you can use direct formula for finding degeneracy. So degeneracy, let's say D equals to 4L plus 2 factorial divided by 4L plus 2 minus n factorial into n factorial. So in short, it is 4L plus 2 Cn. You don't need to remember this, just remember this 4L plus 2 Cn combination formula. L is the orbital quantum number. Orbital quantum number. And what is n? N is the number of electrons. Total number of electrons in the orbital. Now here you see 3 plus 5 plus 7 plus 1 plus 3 plus 5 plus 3 plus 5 plus 7 plus 5 plus 7 plus 9. That will add up to 60. With this formula, let us try to get whether we get 60 or not. Okay. As I don't have space here, I am just showing you it here. Okay, in the next page. So let's calculate for the case of 3p 3d. 1 electron of 3p, 1 electron from 3d. So for 3p, for the electron of 3p, what is the L value? 1. How many electron? Only 1 electron, so N value will be 1. So degeneracy will come from this 4L plus 1 Cn. This is the formula, right? 4L plus 2 Cn, sorry. So 4L plus 2 is 6C1. 6C1, this is equals to 6. Let's talk about 3D. How many values of L? What is the value of L? L is equals to 2. How many electrons? 1 electron. So the degeneracy for this is 4L plus 2 Cn. So 4 into 2 plus 2, 10. C1, that is 10. So total degeneracy D is equals to D1 multiplied by D2. 6 into 10, 60. Okay. Using this logic, can you find out the degeneracy of the spectral tram 3D? total number of electrons. So here only 2 electron, no, 1 electron in 3p, 1 electron in 3d. So for this 3p, when you are calculating 3p, n equals to 1. When you are calculating for 3d, n equals to 2. Look, this is just a short trick, a short formula. Actual case is this. If you are not sure about this, you can use this. You find out these terms, find j values, and corresponding to one j value, it will be get splitted into 2j plus 1 sub. These are levels, 2j plus 1 sub levels. Okay. So for this question, you have to find out the degeneration of the spectrogram 3D. So do it. How A? It is 3D. Okay, not this 3D. 3 you can see it is up. This is 3D. This is a term. You know the difference between term and these things. J value is not there. You have to find out the j values. And each j value, you evaluate from this the j values. Each j values will be splitted into 2j plus 1. So add all of them. How many j values you get? Each j value will be splitted into 2j plus 1. That will be the degeneracy for each j value. So whatever, how many j values will be there for each of them, 2j plus 1, 2j plus 2, 2j plus 1, 2j plus 1. You have to add them all and you will get the total degeneracy. Okay. So it is this situation is like this. This is the term 3D, let's say. Then let's say you get different j values and corresponding different j values you will get, and this each j value is splitted into 2j plus 1 different values depending on. So you have to count these final numbers. Okay, I'm just giving a rough example. So let's say this is 3D and you will get 3D, let's say J1, 3D, J2, 3D, J3. Then this J1 is, this is 2J1 plus 1. Let's say this is 2J2 plus 1. And this is 2J3 plus 1. And if we add all of them, that will give you the total degeneracy. D. Joel, option B you are getting. Very good. Others, what are you getting? So how to get the J values? So you are given 3D. So 2s plus 1 is 3. That means S is equals to 1 and D means L is equals to 2. So J, L minus S, 12 plus S. So 1, 2, 3. So degeneracy will be J1, J2, J3, 2 J1 plus 1 plus 2 J2 plus 1 plus 2 J3 plus 1. So 2 into 1 plus 1, 3. 2 into 2 plus 1, 5. 2 into 3 plus 1, 7. 8, 7, 15. Option B. Is it clear to everyone, or is there any question? Tell me. I hope this is all clear. So when you are will be seeing non-equivalent electron, you can use the degeneracy formula. Otherwise, you can manually calculate. It is not difficult to calculate manually. Let's go for selection rules for LS coupling. Selection rules for LS coupling. You know about parity, right? If you calculate minus 1 to the power L, that gives you the parity, right? If L is even, then the parity will be positive. If L is odd, parity will be negative, right? Now we'll consider the selection rules for LS coupling. Let's consider for one electron atom first. For one electron atoms. For one electron atoms, what will be the LS coupling rules? Firstly, the parity. The parity of the wave function must change. Just write couple of rules: odd to even and even to odd as well. No restriction on total quantum number n. Third one is very important, delta L value. It should be plus minus 1. This is not 0. Delta ms, this will be equals to 0. One electron atom without spin. E. Delta ml is equals to 0 plus minus 1. Delta J is equals to 0 plus minus 1, but J is equals to 0 to J is equals to 0 not allowed. Delta Mj 0 plus minus 1. Just note down these rules. This is for one electron atoms. One electron transition, these rules should be followed. Let's go for two electron atoms. Two electrons are involved. So here change in L value for the first electron plus minus 1, change in N value for the second electron may be 0 or plus minus 2. So if we have a transition involving two electrons simultaneously. Then what will happen? Then delta L must be even for one electron, as you can see 0 or plus minus 2, and odd for the other. Now you see, for one electron transition we have delta L is equals to plus minus 1. So for two electron transition, what will be the case? Look, since we have delta L is equals to plus minus 1 for one electron transition, and the rule says the delta L must be even for one electron, odd for other. So delta L equals to plus minus 1, this is odd for one electron. So for other electron, what will be the condition? For a two electron transition, we have the one electron condition, delta L1 is equals to plus minus 1, and the next, for the next one it will be even. So odd, and these are even. Let's take an example. So we are considering a double electron jump, a double electron jump may take place from the configuration let's say 3D 4D. To 4S 4P. Okay. So how many transitions may be possible here? So there are two possibilities. Number one, you see this 4D electron may go to 4P. So 4D to 4B, what is the change in L for the first electron? 4D to 4P, D to P. So D is L is equals to 2, P is L equals to 1. So final minus initial 1 minus 2, that is minus 1. And let's say 3D to 4S. 3D to 4S, what is the change in L? 3D to 4S, S L is equals to 0, D L equals to 2. So 0 minus 2, that is minus 2. So this is even. Another possibility, it may be 3D to 4P. 3D to 4P. In this scenario, what is the change in L? Minus 1. And maybe 4D to 4S. Here, what is the change in L? Minus 2. Is it clear or not? This is a double electron transition. For a single electron transition, change in L should be plus minus 1. This is important. For a double electron transition, one electron For one electron change, delta L will be odd, and for the other it will be even. That's the rule. Clear, guys? Tell me. So if there is one electron, change in L is always 1. For 2 electron, one electron change will be L value change will be 1, another for another it may be 0 or 2. There is a rule called Laporte rule. What does this rule says? Look, if you are getting confused, you need to revise it once. Okay, after the class you will revise it 2-3 times. I have written it all step by step. You will not get confused. So revise it 2-3 times, then things will be pretty much clear to you. The parity of the configuration must change in an electric dipole transition. Most of the question came from this electric dipole transition. Means if we have odd configuration, odd will be changed to even, or if you have even configuration, it will be changed to odd. Let me know if you have any question till now. Anyone has any question? In which section? Part B or C? Part C. Atomic question will not come in part B. Atomic questions will come in part C only. 5 marks. Look, rules for electric dipole transition. The first condition is change in delta L. It will be 0 or plus minus 1. Delta S equals to 0. Delta MS equals to 0. Delta J 0 plus minus 1, but J is equals to 0 to J is equals to 0 not allowed. Delta 0 plus minus 1. In 1 electron atoms, delta L is equals to 0 is not allowed. Remember this one. Okay, here we have not included delta L equals to 0 plus minus 1. Okay, why we are increasing the number? Look, the delta ml equals to 0 plus minus 1. Let's reduce the number formula. Let's go for some problem that will give you the test of this formula. Which one of the following is an allowed electric dipole transition? Allowed electric dipole transition means those transition will follow the selection rules. These are selection rule actually. Selection rules for electric dipole transition. So I hope you now can do it. Which one of the following is an allowed electric dipole transitions? Look, as per Laporte rule, parity must change. Here, note, parity must change. You have to see this every time. And you know what is parity? Parity is determined from minus 1 to the power L. Okay. So depending on the even or odd value, parity will be plus or minus. बताइए दोस्तों क्या होगा इसका आंसर? Hurry up. Look, from this you will get to know the change in S. From this you will get to know the change in L. From this you will get to change the change in G. Okay, this is the spectroscopic term symbol 2S plus 1 L G. Option B is an allowed transition. Why the first one is not right? Because parity is not changing. In the first one, parity is not changing. In the second one, you see the parity minus 1 to the power 1 minus 1 and final parity minus 1 to the power 2 plus 1. So even, so odd to even. So parity is changing. Okay. Change in J 5 by 2, 3 by 2, 1. That also matches the condition of 0 plus minus 1. So this seems to be allowed. For this one, why C is not allowed? 5 by 2 to 1 by 2. So it is more than 1. So delta J is not hold here. For this one, 0 to 0 is not allowed. We have already told you. 0 to 0 must not be allowed. So that is why this is not also valid. Okay. So you understood why the other three transitions are not allowed. Here for this one, delta J is equals to 2. That is not allowed. Clear दोस्तों? Let's move on. The number of spectral lines allowed in the spectrum of 3 2D to 3 2P transition in sodium each. So 2D terms, 2P terms. 2 terms you are given. So let's say this is your 2D term, this is your 2P term. 2D, 2P. Now we can find out the J values for 2D. What will be the terms? Okay, you try first. If I tell you the answer, then you will not learn. Just separate these lines. 2D, how many components will be there? 2P, how many components will be there? And then you can consider the selection rules. Actually, you have to find out this. You have to consider the transition which are allowed, and from that you can get the number of spectral lines. Okay, very easy. आप लोग वीडियो लाइक नहीं करते हो दोस्तों. Hurry up, why is it taking too much time? 2D, what are the possible J values? 2 means 2s plus 1. S is equals to half. L is equals to 2. Half and 2. 2 minus half, 2 plus half. 3 by 2, 5 by 2. 2P. S equals to half, P equals to 1. So 2 minus half, 2 plus half. So 3 by 2 and half. Isn't it? So it will get split into 2 lines. This will again split it into 2 lines. 2D, 5 by 2, 2D, 3 by 2, 2P, 3 by 2, 2P. Option B you are getting? Very good. Option B. Now 2D 5 by 2 to 2P 3 by 2, is it allowed? Is it allowed? D2P, change in parity is there. 2D 5 by 2, 2P 3 by, that is allowed transition. 2D 3 by 2 to 2P 3 by 2. Here also delta J is equals to 0 and D2P parity change. So this is allowed. 2D3 by 2. So 2P half. Is it allowed? Yes, it is allowed. Now, is anything allowed? 2D5 by 2 to 2P half. Is it allowed? 5 by 2 and half. Half minus 5 by 2. So that is delta J is equals to 2. So this is not allowed. Okay, na? So only 3. So I hope you will be able to tackle any questions from this. Okay. Let us now go for this JJ coupling. So till now we are dealing with LS coupling. The rules for L and S apply only when the spin orbit coupling is weak. This happens when the energy differences between the fine structure levels within a multiplet are much smaller compared to the separation between different multiplets. That is okay. As we move to heavier atoms, more than 30, the spin orbit interaction becomes significantly stronger. This means the rules for L and S work well for lighter atoms but not for heavier atoms. For heavier atoms, we need to consider JJ coupling. Simple meaning, previously we are considering the coupling between L and S. Now we have to consider the coupling between J. One electron, it will have its L and S and it will have its J. Another electron, it will have L and S and that will have J. So this coupling of J and J is considered in case of this JJ coupling. For instance, in the spectrum of a helium, there is a light atom. There are no intercombination like singlet, triplet transition. But in mercury, that is a heavy atom, these lines are quite prominent. It indicates that for heavy atoms, a concept of LS coupling is no longer valid. Rather, we need to apply JJ coupling. Now, JJ coupling holds for heavier atoms, as I have already told, whose atomic number Z value is more than 30. Okay. So here the interactions between the orbital and spin momentum L and S of a single electron is much greater than the interaction between the orbital momenta of different electrons or between the spin momenta of different electrons. Orbital momentum of different electrons L1, L2, L3 and so on. Spin momenta of different electrons S1, S2, S3 and so on. Therefore, in this case, the splitting of the unperturbed energy level due to the interaction of various perturbation takes place. Firstly, two effects primarily comes in. Firstly, spin orbit interaction. Secondly, residual electrostatic interaction and spin-spin correlation. These two things you need to remember. Spin orbit interaction and residual electrostatic interaction and spin-spin correlation. What is the consequence of the first one? Spin orbit interaction. So, for heavier atoms, we have a stronger spin orbit interaction. So, as a result, what will happen? The orbital and the spin angular momentum vector, each individual electron is strongly coupled together to form a resultant angular momentum J. And it has a magnitude root over J into J plus 1 h cut. So, where J can take L minus half, L plus half, J takes half integral value only. For the individual optical electrons, the level corresponding to all the electrons having their smaller J values has the lowest energy. Okay. L minus half, this one is having the lower energy as compared to J equals to L plus half. Now, this is the consequence of the first one. Second, wait a moment. Okay, look, don't worry too much about the theory. We'll take an example and you'll understand JJ coupling very well. Sound is too much. Okay, optical electron means those electrons are which are involving the transitions. Okay, those are called optical electrons. See, as a result of the residual electrostatic interaction and spin-spin correlation, the resultant angular momentum vector j of the individual electrons are less strongly coupled with one another to form the total angular momentum vector j of magnitude root over j into j plus 1 h cut, and the value of j is, you know, for different electrons we have different j values, j1 plus j2 plus j2. So from a minimum value with an addition of 1 unit every time, it goes to up to a maximum value of j. Okay, so don't get bothered about the theory. I will provide this PDF about the theory. Let us take an example to understand what is actually happening in JJ coupling. That will be more efficient for us. Okay, so let us consider the terms for the electron configuration of 4p 4d. We have done it in LS coupling. Now we'll do it for JJ coupling. So 4p 4d, this one we are considering. So for the p electron, you know the L value, it is 1, S value is half. Okay, for the d electron we have the L value 2, S value half. So what is the j value? We will write j1. Instead of writing j equals to L plus S, we will write j1. This is for the first electron. It can take values L1 plus S1 to L1 minus S1, right? So it can take half and 3 by 2. Here j2, it can take values 2 minus half, 3 by 2, 2 plus half, 5 by 2. Okay, now previously what were you doing? You were taking S is equals to something, then L, then you find j. Here the combination of j will be considered. This gives 4 combinations, 4 j1 j2 combinations of the possible j1 and j2 values. Okay, these are, you see, you can imagine it in this way: half 3 by 2, half 5 by 2, 3 by 2, 3 by 2, 3 by 2, 5 by 2, 4. So one will be half 3 by 2, half 5 by 2, 3 by 2, 3 by 2, and 3 by 2, 5 by 2. So we can say thus the spin orbit interaction, this is because of the spin orbit interaction. The spin orbit interaction splits the energy level of 4p4d, energy level unperturbed, energy level into 4 levels. Of which one is lying lowest? Half 3/2 lies lowest and 3/2 5/2 lies highest. Now further, depending on the J values, this can be splitted. Each of the above 4 levels is further splitted by, look, because of the first consequence, spin orbit interaction, we get 4 J values. Now this residual electrostatic interaction and spin-spin correlation, this will cause further splitting. And we have seen that because of the residual electrostatic interaction and spin-spin correlation, the J values gets combined. Okay. Further splitted by residual electrostatic interaction and spin-spin correlation. Into a number of J. Okay, and you can see the values of J, J1 plus J2. So the minimum combination out of the J1, out of the J's, and separated by 1 unit, you will have to go up to the maximum out of the J's combinations. Okay, into number of J levels, and that is equal to the number of, as I have told you, it is separated by 1 unit. You see, it is a minimum plus 1, next will be plus 2, plus 3, and so on. Number of integrally spaced values of G that can be formed out of 2 J values. Here only 2 J values are concerned. Okay. So what we have got? We have got these 4 J1 J2 combinations. From these J1 J2 combinations, we will get the capital J values. The above 4 J1 J2 combinations give J values as follows. You see, half 3/2. What it gives you? You have to form the minimum out of it with modulus and maximum out of it. So half and 3/2. What is the minimum? 3/2 minus half. That is 1. 3/2 plus half, 2. Half 5/2. It gives J is equals to 2 and 3. Next, 3 by 2, 3 by 2. What does it give you? 0. 3 by 2 plus 3 by 2, it is 3. So 1, 2, 3. Integrally spaced, different by 1 unit. Then 3 by 2, 5 by 2. So 5 minus 3, 2, 2 is 1. So 1, 2, 3, 4. Okay. So if you summarize overall, and if I show you in picture, so this was our 4p 4d level. Okay. And this 4p 4d level, because of the spin orbit coupling, we are getting 4 different J1 J2 combinations out of it. 2, 3 and 4, right? So this is your 4p 4d. Originally it was there. Then we're getting the possible J1 J2 combinations. J1 J2 combinations. So this 3 by 2, 5 by 2 lying top. Then we have 3 by 2, 3 by 2, then half, 5 by 2, then what remains? 3 by 2, half, 3 by 2. Now how many different combinations it gives? The first one, 3 by 2, 5 by 2, it gives you 4 combinations. 1, 2, 3 and 4. Similarly, this one 3 by 2, 3 by 2, this also gives you 4. 1, 2, 3 and 4. This one gives you half, 5 by 2, this gives you 2 only. 1, 2, this one gives you 2. So these are the combinations of J1 J2 halos. In here we will be writing the J values 4, 3, 2, 1. Here 3, 2, 1, 0. This is 3, 2, 2, 1. And this is written in this way: 3 by 2, 5 by 2, and in comma you can write 1, 2, 3, 4. For this combination, what you can write? 3 by 2, 3 by 2, 0, 1, 2, 3. For this combination, we can write half, 5 by 2, 2, 3. For this combination, you can write half, 3 by 2, 1, 2. Total number of final levels 4. What is the total number of final levels? 4 plus 4 plus 2 plus 2, 12. which is same as the LS coupling scheme, isn't it? J values are also same. The way, if you have used LS coupling, let's say, you would have got the same J values which you have got here, 4321, 3210, 322, 12 J values you have got for JJ coupling. If you proceed with LS coupling also, you will get same number of J values. Okay. So रिश्ता वही, सोच नहीं. Anyone has any doubt, tell me. Otherwise, I am giving you a doubt or question. Do this one. The J1, J2, J arising from 2s1, 3d1 electronic in JJ coupling scheme are. Oh, we are almost at the end. Tell me, guys, for 2s1, 3d1 electron. What will be the correct option for the JJ coupling scheme? Hurry up. Joel, Murli, Ajay, Vantage, Karthik, Harry. What is the answer for this question? Option A, Vantage, very good. मुझे भी वही लगता है, ऑप्शन ए ही होना चाहिए. 2s3d for s electron, L1 0, S1 half. For d electron, L2 SPD 012, S2 half. So J value Here how much? The way we have calculated in the beginning, in the last case, same thing will be only one value, half. J2 2 minus half to 2 plus half, 3 by 2, 5 by 2. We have to consider J1, J2 combinations. So half 3 by 2 and half 5 by 2. Okay. And if you consider J1, J2, J, so half 3 by 2, 2, 1, half 3 by 2, 2, 1, and here half 5 by 2, 2, 3 or 3, 2. Option A. Option B कैसे मिल गया कार्तिक? So I think you can easily solve question if you get any question from JJ coupling, LS coupling. You just need to revise it, okay? Otherwise you will just mess it up. If you revise 2-3 times, you can easily distinguish between LS coupling, JJ coupling. So always try to remember with some example. The way we have done, we have taken example, illustrated it. So you have to practice, okay? Revise every time. And one thing I would like to tell you guys, your exams are approaching. So try to solve as many questions as possible. So I think all of you are enrolled in the test series. So solve the test series questions, okay? Start from single unit test, 10 single unit test, then go for bi-unit test, then go for tri-unit test. Look, those tests has very important questions. The questions are designed in that way that it will automatically get you covered the syllabus. Okay, if you solve those questions, your syllabus and important topics will be automatically covered. So single unit test you will solve, bi-unit test, then tri-unit test, then half syllabus test, then you will go for full length test. 10 full length mock tests have been uploaded, and every Sunday we are taking Sunday test. Sunday test also has very good questions. So try to solve as many questions as possible. Okay, don't get trapped with the theory part. You will be lured to think that if we practice or revise more and more theory, that will strengthen our preparation. That is not the case. Your preparation will be strengthened if you practice enough questions. Okay, the more you practice questions, the stronger you get into your preparation. Remember this one. Otherwise, if you just keep on reading things, keep on reading theory, you will never be satisfied with that. The best possible way is whatever theory you have done, okay, that is okay, make short notes, revise them, and try to solve as many questions as possible. Okay, and I have already given you the test series, so you have a lot of new questions. Okay, so there is no issue. Okay, occurrence of JJ coupling. Pure JJ coupling is relatively rare. There is a gradual transition from LS coupling used for lighter atoms to JJ coupling as considered for heavier atoms. This shift happens because the spin orbit interaction becomes stronger in heavier atoms, and that is, the first cause, spin orbit interaction. The second cause is residual electrostatic interaction and spin-spin correlation, making LS coupling less applicable. Selection rule for JJ coupling: for electron, the change in total angular momentum J for the jumping or transitioning electron may be 0 plus minus 1, delta J equals to 0 for other electrons. For the atoms as a whole, the change in total angular momentum delta J for the entire atom could be 0 plus minus 1, but for J to 0, J equals to 0 to 0 is forbidden. So these are not so important, but for the sake of completeness, just provided you, and I will provide you the PDF in the course folder. Okay guys, so this is all for this lecture. I think with this we completed LS-JJ coupling and term symbol. In the next lecture we can consider maybe G-man effect. Hyperfine structure is there. We'll go for hyperfine structure, then we'll go for Zeeman effect and molecular physics, and after that condensed matter physics and all. Okay, thank you very much for joining this session. I hope you find this session useful and everyone like the video. Okay, bye bye, take care, have a great day.